By now, you're all experts at taking derivatives. Right, so now we're asking to reverse the process by taking antiderivatives, which can be a much trickier task. At least we don't have as extensive a set of algebraic rules for taking antiderivatives. But the concept is pretty natural. So imagine that you have a complete record of your car's odometer readings over time. Then in principle, from this you can reconstruct the speedometer readings. The velocity, after all, is just the derivative of position. Now we want to reverse this by giving you a complete record of the car's speedometer readings. And we're asking you for the odometer readings at each point in time. And this requires finding the antiderivative. We don't have nice formulas, at least most of the time, but they do exist in some form, even if it's just a numerical form, like a table of values from a graph. By the way, I'm going to apologize for this picture. There was an old joke going around when I was a student, so it's a pretty old joke. Also was pretty dumb, but I guess I need to mention it at the end of this video. So first, let's talk about the question graphically. You should know by now how to take derivatives graphically. We start with a function. I'm going to call this capital F and take its derivative, and I'm going to end up calling it little f. So at each point, I measure the slope from the first graph, slope of the tangent line, and then I plot those values directly below. And it helps to maybe break up the original graph into subintervals using the points where f has local extrema and inflection points. On the first subinterval, f is increasing, concave down, so its derivative is positive and decreasing. At the point where f has a local maximum, the derivative becomes 0. Now on the second subinterval, f is decreasing, concave down, so the derivative is negative decreasing. And this looks to me like the steepest part of the top graph, so that would give the derivative an absolute minimum at this point. Next, f is decreasing, concave up, so the derivative is negative but increasing. Again, when f has a local minimum, its derivative becomes 0. Next, f is increasing, concave up, so its derivative is positive increasing. We hit an inflection point in the top. Now f is increasing, concave down, so the derivative is positive and decreasing, but not all the way down to 0. The slope of f increases again, which we indicate in the bottom graph. Now f reaches another local maximum, so its derivative goes down to 0. F decreases, concave down, so its derivative is negative and decreasing. Finally, f decreases, concave up, so its derivative increases but remains negative. So from the graph of the capital F, we get the graph of a new function, the derivative, which I call little f. I've described the process qualitatively, but this process can be done very accurately and to scale if you make careful measurements of the slope on the top graph to give the values for the bottom graph. Now we want to reverse this process. So we're given the function little f. Its graph is shown on the bottom. I want to find a function whose derivative is little f. I'm not taking a derivative. I'm doing the opposite. I'm finding a new function whose derivative is little f. Again, it helps to break up the domain, this time at the points where little f has intercepts and local extrema. These will become the local extrema and the inflection points for the top graph. But I still have a problem. I need to be given 1 point for the top graph, otherwise I don't know where to start. And if the top graph is shifted up or down, it won't change the derivative. So let me suppose that the top graph goes through this red point that I've shown. Now the top graph needs to go through that red point, increasing and concave down, something like I've shown. I need to indicate a local maximum on the top graph since its derivative becomes 0 at that point. Now the top graph needs to decrease, concave down, since its derivative is negative and decreasing there. Now we reach an inflection point on the top, since the derivative has a local minimum. Next, the top graph decreases concave up, since its derivative is negative and increasing. We reach a local minimum on the top graph where the derivative changes sign. The top graph is increasing concave up, since the derivative is positive increasing. Then another inflection point on top. The top graph is increasing concave down due to its derivative being positive but decreasing. The slope of the top graph increases again. The top graph continues to increase, but its slope reduces to 0 at the new maximum. After the local maximum, the top graph decreases again, since its derivative is negative. We reach another inflection point, where the derivative bottoms out. And the top graph decreases, concave up, while its derivative is negative but increasing. We have reconstructed the graph of capital F from its derivative, little f. Again, it's possible to do this pretty accurately if we're careful in our measurements. But again, the graph of the antiderivative depends on which starting point we chose. If we start with this green point instead of the red point, it will shift the entire graph of the antiderivative down, like this. And for the scale I used, this is the original graph of f shifted down 7 units. The green graph has still got the same derivative, little f, since subtracting 7 doesn't change the derivative. This blue starting point gives another antiderivative, capital F plus 2. And this orange point gives another antiderivative, capital F minus 13. Now let's establish some notation and terminology for what we're talking about. If the derivative of capital F is little f, then capital F is the antiderivative of little f, and we write this notation for that. We introduce the curly S notation for antiderivatives. The notation looks mysterious at first, but trust for now that it's all there for a reason. The curly S and the dx are not just for decoration. It does make sense in ways that it's still too early to reveal. But yes, the curly S really is just a stylized letter S. Notice the differential dx, and it needs to be there. We're actually multiplying f of x times dx. Here's an example. You know the derivative of e to the x squared is 2x e to the x squared, derivative with respect to x. So the antiderivative with respect to x of 2x e to the x squared is e to the x squared plus an arbitrary constant c. Now we say that e to the x squared is an antiderivative, whereas e to the x squared plus c plus constant is the general antiderivative. So when you take a derivative, there's only one derivative, but when you take antiderivative, there are many choices, all shifted up and down by an arbitrary constant. If you fix the constant, then you've chosen a particular choice of antiderivative. How do we know that all the derivatives of little f are simply found this way by shifting up and down by constant? Because of that theorem we saw in a previous video coming from the mean value theorem. So if capital F is an antiderivative, one choice of antiderivative, then it has the same derivative as e to the x squared. So capital F and e to the x squared must differ by a constant. Now, you can take all kinds of formulas for derivatives, you know, and turn them around to get formulas for antiderivatives. And these are just a sample of some of the formulas you get by doing that. As in my previous video, there are many pitfalls to be aware of, but to mention one common pitfall, many students at this point start getting the formulas backwards. So they end up taking a derivative instead of antiderivative, or antiderivative instead of derivative. A little bit of notation to be aware of here. When f of x has the form of a fraction and you're multiplying it by a dx, sometimes we just find it shorter to write the dx in the numerator. You're just multiplying after all. And here are a couple formulas you can write that way. And for example, antiderivative dx without anything there, that's a 1 times a dx gives dx. And the antiderivative then is just x plus a constant. And again, we can use this shorthand when talking about the antiderivative of 1 over x dx. That's just antiderivative dx over x. And we know the derivative of natural log is 1 over x. So antiderivative of 1 over x should be natural log plus a constant. Well, of course, this only works when x is positive. And that's not quite as much as we could say, because the function 1 over x has domain all non-zero x values. So we want an antiderivative that's defined on the same domain, not just for positive x. So how do we find that? Well, you look at this function, natural log of absolute value of x. So here we mean you take natural log of x when x is positive. You take natural log of negative x if x is negative. This is now defined for all non-zero x values, and you can check that its derivative is 1 over x. So for x positive, it's the same thing we had with derivative of natural log. If x is negative, you need to use the chain rule, but 2 minuses make a plus, and again, the answer comes out 1 over x. So now we have an antiderivative that works everywhere in the domain, everywhere where x is not 0. But actually, that is not the general antiderivative. It's not the most general antiderivative. There are others, and you should recognize here that since the domain is not an interval, it's a union of 2 intervals. You've got an interval where x is positive, another interval where x is negative. Well, you can take the graph on the right-hand side and shift it up or down by a constant. You can take the graph on the left-hand side and shift it up or down by a different constant, and you're still going to have a function with the same derivative. So this fact was pointed out in our earlier video following the mean value theorem. We explained if 2 functions have the same derivative, you can conclude they differ by a constant. That's only, however, true when the domain is an interval, and if it's not an interval, if it's different intervals put together, then you can shift up or down different amounts on different intervals. Now you know how to find antiderivatives of all powers of x, and it's neat to see how the formulas we have complement each other. When the exponent, I call k, when that exponent is -1, the first formula can't work, because then the denominator, k plus 1, would give you division by 0. But fortunately, you have a different formula in that case, which comes from natural log. And again, for reasons I described on the previous slide, this formula I'm showing you here is actually an oversimplification because of what happens when x is negative. Now, our notation actually has a product of f of x times dx. So, well, can I just write it this way with dx times f of x instead? Textbooks today don't usually do this, but yeah, this is still correct. And some old books in the past, different authors have actually preferred this notation. It's not one that necessarily you want to go with, but it is correct. Here is an example of using the previous slide to get the antiderivative of a polynomial, and you can just do it term by term, like I've done here. Notice the use of parentheses here, and anytime you multiply things and you want to multiply the whole thing, you want to multiply this whole polynomial times the dx, not just the 1 times dx, then you need the parentheses. They need to be there. I'll just remind you that square root is really a power function, so you can use the previous slide to get that antiderivative as well. Now it's time I mentioned that x is not the only variable you can use, and here I've expressed the previous statement using a different name for the variable. Everything works just as well with t instead of x, or u, or v, or w, or whatever variable you want. Now, there are lots of tricks for finding antiderivatives, and most of them we won't get into in this course. You'll need a later calculus course to get there. But I'll tell you that by far the most helpful technique is one that you can start using right now, and it's simply called inspection. I call it guess and check. So for example, we want the antiderivative of 3x plus 1 to the fourth. Now, we have a feeling the answer should be something like 3x plus 1 to the fifth. But with possible constant factor, which I'm missing, I'm aware that there is a constant factor coming out because of the power rule, but also there's another constant factor coming out because of the chain rule. And now that's too much for me to guess right off the start. So I just make a guess like 3x plus 1 to the fifth, and now I just check the derivative of that and see what I get. Derivative of 3x plus 1 to the fifth, first of all, a 5 comes down because of the power rule, but then there's another 3 gets multiplied because of the chain rule. Altogether, 15 times 3x plus 1 to the fourth. Well, that's 15 times what I want. So I just divide both sides by 15. And that gives me the answer. So if you're up to snuff on taking derivatives, there's really no reason to write down a wrong answer for one of these antiderivative problems, because you simply check your answer by taking a derivative. And you might try several guesses. You might take several minutes guessing, but then it should only take a few seconds to check the answer by derivative. So you should really be checking your answer every time. Every time you work out an antiderivative, check your answer by taking a derivative. Please check your answers. And I always tell my students, if they check their answer and find out it's wrong and say that, that's worth a lot more than if they got the wrong answer and didn't check anything at all. Here's another guess and check. This one is a little more involved. I want the antiderivative of x times e to the 2x. I'm going to guess x e to the 2x. Make your first guess really simple and don't worry about constant factors or anything. You can worry about them later. The reason I guess this is because I know the derivative of e to the 2x is almost e to the 2x, and so the antiderivative is again almost the same thing. I know this can't be exactly right, but I'm going to check and get it right. So I check the derivative of x e to the 2x from the right hand side, and that derivative I need the product rule, and that gives me, oh well, look, the second term from my product rule, that's almost what I really want. The first term is the first thing I'll need to deal with, that exponential for the first term. So I need to get rid of that. So I update my guess. I revise it by subtracting off something that is designed to kill off that lone exponential term. So I managed to do that. Now I have something that's only off by a factor of 2. It's just 2 times what I want, so I divide both sides by 2. And now I'm there. So my third guess, and I'm there. So that gives me my antiderivative. And it's really straight from the previous line, except that I've factored it into a nicer form, easier to read. Now, I should caution you that straightforward formulas for antiderivatives are not always available. Try as you may. Here is the first example I showed you. Antiderivative of 2x e to the x squared is something simple. You might think that if you took out that 2x, that should make it even simpler, but it doesn't. It makes it impossible. Really impossible. So antiderivative of e to the x squared is not something you're going to find in any simple way. What I'm saying here is that this antiderivative does not have a nice answer that you can simply write down or evaluate using most calculators using notation that you're familiar with. So to be sure, I can tell you there is an antiderivative, but there just isn't any simple way of writing that, expressing it using the language, the notation, the functions that we have learned to work with, trigs, exponentials, polynomial stuff. Well, there's no real reason to expect a nice way of writing a function like this. You know, most functions in real life do not have nice formulas using polynomials, exponentials, log, trig, etc. That's just life. And this is not just a problem for e to the x squared. Most functions do not have a nice expression, and most of them do not have a nice formula for their antiderivative. You might get a wrong impression from the nice formulas we did for derivatives, but you know, for antiderivatives, there are not such nice formulas in general. By the way, most students seem to not believe me here. They think they should be able to find a reasonable expression for this antiderivative of e to the x squared. If that's you, then I suggest you try your hand at it, guess and check, and after a little while, you'll start to believe me. And actually, when I say there is no simple formula for this antiderivative, no so-called elementary formula, I mean, I know that because it has been proved. I've actually given the proof in class, not calculus class, of course, but in algebra class. So it does require abstract algebra to understand which functions have so-called elementary antiderivatives that you can write down with expressions that we're used to. Okay, I guess before signing off, I've got to quickly recall these old jokes. The integral of 3 ice squared d ice is ice cubed. Okay, well, think about it. And then if you take antiderivative of 1 over cabin, right, times d cabin, the answer is natural log cabin. So I guess that's log cabin made from natural logs. Yeah, okay, well, I'm forgetting the plus c. So if I put in plus c, what's a log cabin plus the c? That's, I guess, a houseboat. And, well, okay, I guess it's probably time to make a quick exit.